Welcome to another lecture on methods in quantum mechanics. We've been talking about the variational method. 2 classes ago, I introduced the method to you with some simple examples, and then we talked about the helium atom. And today we're going to talk about the hydrogen ion molecule, which is the simplest case where there's chemical bonding. This is section 8.3 in Griffiths, and I encourage you to work through it with a pencil in your hand and work out some of the details that are in there. You would spend a long time working out every step of the derivation that's outlined in that section, but I really got hung up on equation 845, and so that's what I'm going to focus on here is where in the world does the Hamiltonian expectation value come from in section 8.3. To review the variational method, the first thing you do is you write down the Hamiltonian, and you do need good information on the system in order to write that accurately, the kinetic plus potential energy, and then you take your best shot at a ground state wave function. I got that highlighted in red for a reason. It's really important. You're only going for the ground state here. How do you guess the ground state wave function? You write a function that has large amplitude where the potential energy is large and negative, and has small amplitude where the potential energy is in the way of the particle. For example, if a particle encounters a barrier, the probability of it being beyond that barrier is very small, so you would write a wave function that has small amplitude in the barrier region. You include a parameter in your wave function. I just said lambda for the sake of saying something here, but in fact in today's example we'll call it big R. But you include a parameter. It's not a variable. It goes through the whole calculation as a constant. And then when you get all done, you find the energy eigenvalue, which includes that parameter, and you differentiate that energy eigenvalue with the parameter in order to find the value of the parameter where the energy is a minimum, and that's your best estimate of the energy eigenvalue. You'll get something that is always greater than the true energy that's actually built into the variational theorem. It will hopefully be close. The more accurately you guess the wave function, the closer it will be. So here's the hydrogen molecule ion. You have 2 protons and only 1 electron. So you start off, say, with a neutral hydrogen atom, a proton and an electron, and then you bring in a second proton. And if you bring it in close enough, we have this question: is there a proximity where that proton actually feels comfortable and will just stay? Because if it's really far away, it'll just hang out by itself and say, I'm happy alone. If it's too close, it'll feel the repulsion of the other proton and leave. But is there a value of big R where the 2 protons actually are in some sort of an equilibrium and this system maintains itself? Little r is the distance from one of the protons to the electron. Little r prime is the distance from the other proton to the electron. And hopefully the angles are fairly self-evident, what theta is. Phi is the rotation about the axis that's in the screen. So it's actually the usual spherical coordinate theta and phi. What does the electron Hamiltonian for this system look like? That is the Hamiltonian that describes the electron's energy. You have the kinetic energy operator, and that electron feels electrostatic repulsion between 2 protons. And so you write minus e squared over 4 pi epsilon naught r for 2 of those. Remember, the potential energy is electrostatic. It's just an r, not an r squared. That's the electron Hamiltonian. The 2 protons also repel each other, and so they too have some energy, and there is an extra term you might consider adding at this point, but we're going to hold off on that. But do make a note to yourself, you should actually add plus e squared over 4 pi epsilon naught big R for the electrostatic attraction between the protons. But instead we're going to insert that way at the end. For now, we're just going to talk about the electron Hamiltonian. We need to guess a wave function to start with. So I'm going to go out on a limb here and say what I see is a hydrogen atom, and I see another hydrogen atom. The only thing is they're sharing an electron. I'm going to write the wave function as the combination of a hydrogen atom wave function for this electron pairing up with the proton on the left, and a hydrogen atom wave function for the electron pairing up with a proton on the right. And I will put normalization in front. And by psi 0, I literally mean the ground state of hydrogen. That's my starting point. It's my first best guess. What we're going to do at the end is we'll see how close our estimated energy is to what's been measured. And when we get all done, we're going to have a length, big R. And we're going to see how close that is to what's actually measured. About the normalization constants, we can treat them as parameters in this variation. There are actually three things we should consider, those along with big R. So that's three variational parameters. You can go through optimizing these A1 and A2s, maybe keeping R fixed, and first see what A1 and A2 have to be. Can you guess what A1 and A2 will need to be? Well, you look at this hydrogen molecule with one electron. I don't see any reason for the left proton or the right proton to be favored. This electron is just there, and it will call either one of these home equally. So my take on that is that A1 and A2 will have to be equal. And in fact they are. So I've seen variational method calculations on A1 and A2 which come to the conclusion that A1 and A2 have to be equal. It makes common sense, and it can actually be shown with the variational method. We're going to go ahead and just use that, and we're going to focus on big R. So let's find what this A needs to be. So rewrite the wave function that way, and we'll normalize it by saying 1 is the integral of psi star psi. Well, nice thing about this problem is the wave function is real. Keep that in mind. The wave function is real. That's going to simplify some things later on. So this wave function just squared with itself. You have three terms. First integral, I hope you recognize immediately, is 1. A psi 0 squared integrated over volume. Let me explain the d cubed r, what that's all about. That's a volume element. It's a volume element. I had to pick one of the protons to be the reference frame. And we're using the Born-Oppenheimer approximation here, that the protons are just staying put in place. And the second integral as well should be 1. We're using the ground state wave function of a hydrogen atom. It's already normalized. I'm not even going to compute these. That's the difficult one. So the overlap integral, the integral that has the wave function for the electron with one of the protons times the wave function of the electron with the other proton. Integrating that is a bit of a bear. I write this out explicitly as an integral. You've got the coefficient in front squared, but then you have the exponentials multiplied by each other, and that's it. You integrate it over a volume with the usual spherical coordinate boundary conditions. Griffiths outlines the solution here. What's difficult is you have two r's, r and r prime. And dv is in either system. I may as well just use r. So dv, what is dv? It's sine theta d theta, r squared dr, d phi. That means then that the other one, r prime, has to be written in terms of it. So employ the law of cosine, and you get r prime written in terms of r. And you can go back into our integral and insert that in. So put this expression for r prime in right there for r prime, and you've got everything in terms of r. Now I wrote out the differential volume element. The phi integral, of course, is just 2 pi. That's done. The theta integral is a little more challenging. To do a theta integral, you need to do a u sub and then integrate by parts, where the u is what you got out of the law of cosines. And that way you can write du in terms of d theta, and you can proceed from there. You will need to use gamma functions to solve the r integral. Don't have that written there, but just make a note to yourself, solve the r integral. You're going to resort to gamma functions. And 3 pages later, you'll have that the overlap integral equals this expression. You can work that out on your own if you like. I did. It took 3 pages. Okay, so then you can take this overlap integral, you put it back in and solve for a normalization constant. And when you put it all together, you have the normalization constant. A squared is 1 over 2 times I plus 1. We're going to keep just writing A for now. And today what we're focused on is equation 845. Where did it come from? In other words, we need to set up these two integrals, the direct integral and the exchange integral. So the Hamiltonian operator acting on the postulated state looks like this. You have the Hamiltonian operator, and we're going to replace e squared over 4 pi epsilon naught with k just so I don't have to keep writing it. And there's our postulated state. I will keep writing A instead of what we just figured out. Expand this so that you have 6 terms, right? Because there's 3 inside this green parenthesis, and which is everything that's acting on the ket, and there are two terms inside the ket. Make sure that you follow this expansion. I want to make an observation because this can be messy. I look at 4 of these 6 terms, and I recognize something. Do you see what I see? So the first 2 terms is the kinetic energy operator operating on the true wave function, and the second 2 terms is the potential energy acting on the true wave function. Altogether, they are the unperturbed Hamiltonian operating on the unperturbed eigenstate. So I have the unperturbed Hamiltonians written twice, acting on a linear combination of unperturbed ground states. Since that linear combination is normalized, the unperturbed Hamiltonian acting on it is going to give you E1. That is minus 13.6 electron volts, that E1. I will not have to keep writing all of these. I already have a number for those 4 terms, and I'm not going to work them out because I know that I get minus 13.6 electron volts when I use the unperturbed Hamiltonian to act on a linear combination of ground states. By the way, the shorthand will come up again. This e squared over 4 pi epsilon naught that we keep seeing is also minus 2 times the Bohr radius times E1 in the way of this thing. So this simplifies it considerably. The electron Hamiltonian operating on the eigenket is the unperturbed ground state on that eigenket minus just the potential energies that are remaining. You just have these 2 terms left. And so you can keep those 2 terms explicitly stated. Now close the ket. So the bra that we bring in is the trial wave function, and we close the ket with that. On the left side of this equals sign, we just have psi h star psi, which you know that just equals whatever the answer is. That is the energy. And on the right side, we'll do a little bit of analysis here. First of all, you close this psi E1 psi, you get E1 because the E1's a constant. It can come out, and you just have the bracket of psi psi. And that's going to be 1 because it's normalized. The next term gives you 2 terms when you bring this in. So make sure you're following that. And the third term gives you these 2 terms when you bring in that bra vector. So make sure you're following that. That's an R. Let's go ahead and expand out these 2 terms with the 2 wave functions in them so that the second term is actually 2 terms in itself. Psi 0 of R, 1 over R prime psi 0 of R, and so on. So I have not 3 but 5 terms. I recognize something else about these, and it's really bound up in the symmetry of the whole problem. I'll number each of these terms 1, 2, 3, and 4. Are any of these terms equal to each other? Compare 1 and 4. The electron does not favor one proton over the other proton. So R versus R prime, same thing. So this bracket should come out to the same value if you switched all of the R's and R primes with each other. So 1 and 4 are equal just by symmetry. 2 and 3, because 1 over R is Hermitian, we can just move it over and that's a rearrangement of equation 2. And equation 3, same thing. And because the electron does not discriminate between R and R prime, these two brackets have the same value. So I'll just write one of them and put a 2 in front. So I'm going to do that. Here's term number 1, and I'll skip term number 4 and I'll just put a 2 in front of it. And here's term number 3, and I'll skip term number 2 and just put a 2 in front of it. And you have this expression then for the expectation value of the Hamiltonian, which, by the way, if you want to know energy, is kind of the answer. This is called the direct integral because the states that are being integrated are the states for the left hydrogen atom. And this is called the exchange integral because it involves the eigenstates of both of them. Nickname them big D and big X, and actually by convention a factor of the Bohr radius is tossed in there. And so the direct integral is actually this thing times the Bohr radius. You can work them out. I think for homework I'm asking you to solve one of them, whichever one is maybe a little less of a headache. I'm asking you to solve it. If you solve these and put them back into the expectation value of the Hamiltonian, this is where we account for big R. The total energy is the electron Hamiltonian expectation value. That's what the first term here is. Plus the proton-proton interaction. So just toss that in as a Coulomb repulsion between the two protons. And that's E squared over 4 pi epsilon naught R. So I'll point out to you, based on just how E1 is written, the first energy level in the Bohr model is written, you can rearrange these letters to be instead minus 2a E1 over R. And that can be helpful because we already have E1 showing up in here. And so that's the total energy. Let's put it all together. So insert it all in here. The expectation value of the Hamiltonian and that Coulombic repulsion of the protons. And after a lot of just algebraic simplification, you have this expression, where again a squared is the normalization, and it's 1 over 2 times 1 plus I, where I, that integral, was found to be this. That's the 3 pages of algebra integral result. Put those in there, and if you want to know what your answer really is, you still have this parameter big R you have to get rid of. So then you differentiate the energy with big R, set it equal to 0, and solve for big R, and that can go back in to tell you what the energy is at a minimum. The key thing we might want to know is just at what value of big R is the energy minimum, because that's actually the solution, and you'll get 1.3 angstroms. And it's a little off from experiment, which per Griffiths is 1.06 angstroms. You can make a graph of then energy versus R. Rather than doing the derivative, you just graph energy with R in it versus R, and it looks like this. It'll be at 1.3 angstroms where it hits a minimum. Now this picture depicts bonding. Remember, big R is the distance between the two protons. So when big R is infinity, the protons are far apart from each other, way out here. When big R is 0, the protons are right on top of each other. So surely that never happens, and the energy is huge. When that does happen, it's infinite. And when big R is very large, you have the energy of a single hydrogen atom, because you have one hydrogen atom and then you have one lone proton. A proton all by itself out in free space, not moving, has no energy. The only energy is the binding energy of the electron with the other proton. So it's going to be asymptotic at minus 13.6 electron volts. The fact that it dips down to a lower level anywhere between 0 and infinity of big R is evidence that bonding occurs, because now there's a comfortable place. There's an energy minimum. So the second proton gets to be 1.3 angstroms away from the first proton. It's happy, it stays. And like I say, the real answer is 1.06. Think about all of the things we did that are not going to give us the exact experimental result. We estimated the starting wave function as just the sum of two hydrogen atom ground state wave functions. That might not be what it is. Apparently it's a little different, but that's our estimate, and we did the variational method with it, and we got something that was not too bad. And by the way, the binding energy turns out to be minus 1.8 electron volts in that case. In other words, it takes 1.8 electron volts to take an ionized hydrogen molecule and separate out the spare proton. That's the holes I wanted to fill in section 8.3 of Griffiths. Go back through as well and follow all of that. You may want to take a shot at solving this integral I, this overlap integral. But the method that we just employed is linear combination of atomic orbitals. Just make sure you remember that, LCAO. It's where you write a trial wave function for your variational method as a sum of multiple atomic orbital wave functions. And this is an important technique in atomic physics because as you get to more and more complex atoms, you'll be adding up a lot of atomic wave functions.